Saxon Algebra 1, lesson 117. Welcome, my students, to the last week of lessons for this year. I'm excited. I hope you're excited. There's a couple good ones coming up. Do not feel that your efforts are in vain. This is good stuff, and it's going to help so much next year because we're going to revisit these topics, and instead of it being new and coming at you out of nowhere, you're going to be like, oh yeah, I vaguely remember this from the end of last year, and it's going to be so much easier to learn next year. So, lesson 117 picks up on a topic that we talked about quite recently. It's about direct and inverse variations. Remember that was about the toddlers coming in the room and the toys coming off the shelves and the teenage boys eating the pizza. This time we're just going to add one tiny little curveball to it, a little bit of top spin, I should say. Sometimes SQ, that's spelled right. Okay, looked weird to me. You'll see that in these we're going to use the same basic forms of the formula. Is that a word? Kind of. Remember that this is the direct variation formula, and this is the inverse variation formula, where K is a constant. And we do these problems in two steps. First, we fill in an A and a B, and we use that to solve for K. And then we take that value for K, and we get a new either A or B. And we use, let's say it's a new A. We use the new A and the constant that we calculated from the first step to solve for B. Or vice versa, we might have the B and the K and solve for A. Doesn't matter. This is the direct form. This is the inverse form where we divide. And we also talked about the fact that you don't have to overthink this. Oh no, look at the marker. Tragedy. Happily, I have another option right here. You don't have to think too hard about how to plug the sentence into the equations. You just follow the flow of words and put it into that format. So what's going to happen this time is we're just going to have some information about something being squared. And it's usually the B that's squared. So let's just try one and see what happens. Example 117.1. The distance required, okay, this is, they get a little physicsy. Don't let that throw you. The distance required for an automobile to stop is directly proportional to the square of its velocity. Okay, velocity means speed with the weight of the car factored in. Okay, so let me read it again. The distance required for an automobile to stop, D, is directly proportional, so it's this form, to the square of its velocity. Let me read it one more time so you can see how the words match what we wrote. The distance required for an automobile to stop, all those words are represented by D, is directly proportional, so we use this form, to the square of its velocity. It's just a number sentence. Okay, so now if a car can stop in 20 meters, okay, so that's a distance. It's 200, by the way. 200 meters is a distance at 20 kph. Okay, kph is a speed, right? Kilometers per hour, it's like miles per hour. So that's a velocity. What will be the required stopping distance? Okay, so we want to solve for D at 28 kilometers per hour. Okay, so in this case, I can use the units to help me figure out whether it's distance or velocity. Velocity is like speed, so per hour, that makes sense. Distance is just the meters. Okay, so here's my 1 and 2. We'll use this information and this formula to solve for K. So 200 equals K times 20 squared. Plugging in. I use parentheses here to make sure that I know I'm not trying to square the K, I'm only trying to square the velocity part of it. And these are just smidge harder to solve because we have to deal with an exponent, but really, I think we can handle it. 200 equals k times, let's see, that would be a 4 with 2 zeros. Divide both sides by 400. So our k equals, you can do 0.5 or you can say 1/2, whichever makes you feel happier. You know that as scientists, we often go with decimals. As mathematicians, we like to stay with fractions. Either way will work. Okay, so now we're gonna do the next one. What is the distance if, and I'm gonna use the fraction this time, 1/2 times 28 squared. Okay, so we're gonna do it by hand. We're not gonna rely on a calculator. 28 squared, I don't know, but I can sure figure it out easy enough. 8 times 8 is 64. 8 times 2 is 16, plus 6 is 22. And then I put the 0 down. 2 times 8 is 16, carry it as a 1. 2 times 2 is 4, plus 1 is 5. So that gives me 4, 8, 7. 784, and then I need to, I'll just write it so you can see. 1/2 times 784. And then if I divide this by 2, that'll give me the answer, right? Because I have to multiply it by 1/2 or 0.5, either way. So now I'm going to write my answer over here because I don't have room up there. 2 into 7 goes 3 times. That's 6. 18. 2 into 18 goes 19. It comes out even. And I get a 2. So that's the answer when I divide 784 by 2. I ran out of room, but you can see that. And so the distance, the stopping distance required for a car traveling at 28 kph is 392 meters is our unit. Beautiful. Okay, that's the right answer. We don't need to understand the physics, but it does help if we can take the units of the numbers they're giving us and figure out which one of them they are. So we want to use our brain a little bit, but we don't have to understand physics to do these problems. Okay, let's try another one. Example 117.2. Let's see how many there are. There's 3. Hang in there, we can do it. Okay, so I'm gonna write my formulas again up here. When you're doing your homework, please do this every time. Make sure you can see your formulas wherever you're working. So you don't have to write it multiple times on a page if you don't want to. There's no harm in doing that. But make sure that on every page that you're working, you can see your formulas. Okay, the distance a body falls, yikes. I'm assuming they mean a body like an object, not necessarily a human body. The distance a body falls varies directly, okay, so we want this form, as the square of the time it falls. The square of the time it falls. Okay, let me read it again. The distance a body falls varies directly, this form, as the square of the time it falls, okay? And this always reminds me, in college, I studied accounting. I got the job of my dreams. When I graduated, I worked for a big public accounting firm in downtown Chicago. And I was at work one morning and standing and talking to somebody that worked next to me. You know, we had little cubbies. And I'll draw you a picture. Here there was a big window on this wall. And then we had our little cubbies like this, right? There were 3 of them on each side. And mine was the one in the middle. But I was standing and talking to my friend who was sitting in her cubby here. So I was standing where I could see out this window. And it was 8 o'clock in the morning. And as I was standing and talking to her, and we were on what, maybe the 14th floor? I think the 14th floor. A body, a human being fell past the window. There was suddenly just a human being went zipping by the window. And I was freaked out and we ran. My friend and I both stood up and looked out the window and yeah, there was a human being lying in the street down below. It was really, really, really sad. And I always think of that experience when I talk about this, the distance a body falls. So there, did I cheer you up? Did I brighten your day? Whatever your problems are, you guys, they're better than being the person who fell out the window. You can make it. I have great faith in you. Okay, no, but seriously, it was bad. Okay, if it falls 144 feet, okay, so we've got distance and time. 144 must be the distance. It's not the time. In 3 seconds, okay, that's the first scenario. How far will it fall? So distance is what we don't know. In 10 seconds. Okay, I don't know the physics of this, but I know the difference between feet and seconds. And I know which one describes the distance and which one describes the time. That's all the brain power you need for this. So now we do our step 1. We take our formula and we plug it in and solve for k. So 144 equals k times 3 squared. That's 104 equals k times 9. We divide both sides by 9. And let's do that over here. 144 divided by 9. It goes in there once. Subtract and get a 5. 4, that goes evenly. Okay, so k equals 16. Okay, remember that our constant, it's not a unit. It doesn't have to make sense in our problem. It's just the number that links those two. It describes the relationship between them. Okay, so now we can use that the second time to solve for d. So we have d equals 16 times 10 squared. Okay, remember we have to square that because this is our tailor-made equation, formula, I should say. This is our formula for this problem. A formula is the generic form, and an equation is a statement that has an equal sign in it. So this is an equation, but it's more specifically a formula. Okay, so now we just do the multiplication on this, and we can do that in our heads. This is going to be 100, right? A 1 with 2 zeros, and so it's 1620, and it's feet. Dun, 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 dun. That's the right answer. It's always fun when I have a fresh marker. I always feel happier about my life. Okay, so physics in the third one, again, and the numbers are going to get a little bigger. Strap in, hold on, but don't worry. It's not any harder. It's just a little wackier looking. And this is the last one for this lesson. The weight of a body on or above the surface of the earth, okay, so that's a W, we're going to call it weight, varies inversely, okay, so it's this one, with the square of the distance of the body to the center of the earth. The square of the distance. Okay, so what they're saying is that how much you weigh when you stand on the earth, let's put both feet on the earth, has a relationship to how far you are from the center of the earth. So if you're on a bigger planet and it's farther, you're going to weigh something different, okay? We don't need to get into the physics of that, but that's generally what this is saying. Let's read it again. The weight of a body on or above the surface of the earth varies inversely with the square of the distance of the body to the center of the earth. Okay, now our scenarios. If a body weighs 10,000 pounds at a distance of 5,000 miles from the center of the earth, how much would it weigh? Okay, so our second scenario, weight is what we're going to find. At a distance of, how much would it weigh 50,000 miles from the center of the earth? Okay, so it weighs 10,000 pounds when it's 5,000 miles away. How much does it weigh if it's 50,000 miles away? Okay. So again, we now can, now that we've got our sentence arranged and our numbers filled in, we can completely forget about the facts of this, or the physics of this, and just focus on the numbers. So 10,000 equals k divided by 5,000 squared. All right, 10,000 equals k times, let's square this. The 5 squared is 25, and then we square the zeros by duplicating them. 2, 3, 1, 2, 3. Okay. Starting to get a lot of zeros, aren't we? So, oh, my cat wants in. Sorry, he'll knock the screen out if I don't go get him. Hang on. Pause. Talk among yourselves. Sit. Come on, cat. That was a little joke. I know you can't really talk among yourselves. I know you're not sitting at the Ricksman's dining room table right now in your usual seats, listening together to my voice echo from the ceiling, but sometimes I like to imagine that you are. Okay, so we're gonna multiply that times that. Holy smokes, what we're gonna get is a 25 with 6, 7, 8, 9, 10 zeros. So I'm just gonna write it like this. Right? I counted up all my zeros, 6, 7, 8, 9, 10. So that is an easier way to write this in scientific notation. Now notice it's not proper scientific notation because I've got 25 as my lead number. Technically, we would need to make that 2.5 and change this to 10 to the 11th. But I'm gonna skip over that step because I could do this much in my head really fast, and we're not gonna leave it in this form for long. That's not our final answer. So I'm just gonna leave it like this and do part 2 of the problem because the number's probably gonna get even wackier, isn't it? Okay, so now we're gonna say that the weight, we don't know that, W, I'm gonna go over here because I have got a little more room, equals K, 25 times 10 to the 10, divided by D squared. Well, that's gonna be a big number, isn't it? Yikes. Okay, well, we're on the right track, so that's fine. We could multiply that out and leave it as a big number and make this a big number. But what John suggests we do is we keep our numbers manageable by writing this in a similar form to that. So how would we do that? The 5 would square to 25 again. And how many zeros would we get? 1, 2, 3, 4. We would have 8, right? That makes sense? I square this by saying 5 times 5 is 25. I square this, I square all the zeros by doubling them. 1, 2, 3, 4, so I want 8 of them. So now we see our weight equals 25 times 10 to the 10 over 25 times 10 to the 8. 25 over 25 cancels to 1. And then we use the quotient rule for exponents to subtract. That would be 10 to the 10 minus 10 to the 8, so we would be 10 minus 8. So this becomes 10 squared. Makes sense? 10 minus 8 is 2. And so our final answer is 100, and it's weight, so it's pounds. Is our final answer. Yay, I got it right. Yay us, team, okay? So this one isn't really, it's not any harder. I mean, the story's a little weird, the whole thing about the weight and the distance. But once you just sort through the words and find out what the formula is, then the new complicating factor in this problem was just these monstrous big honky numbers. You could have left them big and you would have just canceled a bunch of zeros. That would have been fine, but this is a nice, neat, cleaner way to manage all those zeros. Okay, Lesson 117 is done. Lesson 118, I'm so excited, you guys. I can't wait. It's one of my favorite lessons. It's hard, but it's really fun. Okay, bye.